All right, so let's look at the first set of problems on that page 7. The first set, what were the shapes in problems 2 and 4? What shape did you get when you graphed those? Circles. Circles. By the way, I don't know if I told you this or not. Go ahead and get your calculator out, and let's graph that first one. 5 cosine theta. Okay, that's what we're going to talk about. So 5 cosine theta, we're going to graph that thing. Now, we are graphing on a machine whose screen is rectangular. Right, it's a rectangle. I don't know why they didn't build it as a square. They didn't. So what happens is, when you set your window from -10 to 10, which is logical, that's the standard window, this 10 is stretched more than this 10 is. So everything you graph is warped. If you want an accurate picture, do zoom 5, zoom square, and that will square your screen, okay? So I forgot, I should have told you that before. So anytime that you want to get an absolutely accurate shape, zoom square, and that will square your screen and eliminate that stretch, horizontal stretch, okay? So now it's very clearly a circle. So problems 2 and 4 are circles. What observations did you make about the circles in number 2 and the circles in number 4? Number 2, they're oriented on the x-axis, and on 4, they're oriented on the y-axis. And in number 2, the first one is on the right side, and the second one is on the left side. Now, does all that make sense to you? Yeah, cosines are x's, sines are y's, positives, negatives, right? So for your signs, the positive sign was above, and the negative sign was below. That all good? All right, page 8. Number 7, these were all shapes that involve cosines. So everything you drew in number 7 should have had symmetry on the x-axis. And everything you drew in 10 should have some kind of vertical symmetry on the y-axis. Now, what observations did you make here? These are the really interesting ones. What observations did you make? What did the number out in front? So when you have 5 cosine 3 theta, -4 cosine 5 theta, what did the 5 and the -4, what did they seem to have to do with?
They scale it.
How long? All of these had petals, they were roses, and the length of the rose is that number. So when your equation is 5 cosine 3 theta, that is the length of your petal. So on your polar graph, if this is the 5th circle, these things, I don't know where, they're 5 long. And that makes sense because rectangularly, if I were to graph this cosine curve rectangularly, wouldn't it go up 5 and down 5? So that is like the amplitude. Only since it's circular, it's the distance from the pole. All right? Then what did this guy seem to control? What did he have to do with anything?
If it was odd, then it was the number of petals, and if it was even, then it was 1/2 the number of petals.
so there we go. This controls the number of leaves, or the number of petals. I guess I used petals. And Leo made exactly the right observation. When that number is odd, that's how many petals you got. So this thing, I can tell you right now, without graphing it, it's got 3 leaves, they're 5 long, and it's got symmetry on the x-axis. Now, when I make that, when I go to number, r equals 5 cosine 2 theta, that guy has symmetry on the x-axis still, because he's a cosine. His leaves are still 5 long, but now there are 4 of them. Did you observe that? All right, perfect. And then, did the same rules apply to the sine ones in problem number 10? Yeah, same rules apply, but the figure was oriented differently because it has a different symmetry, because it's a sine. Okay, let's go to page 9. What shape did you observe on page 9 with 2 and 5? It's a lima sign, right? Right? When we talk about those, it's a lima sign. And some of them had interior loops, and some of them didn't. What was the big difference between number 2 and number 5 in terms of the way they were oriented? Number 2, they were all oriented sideways. And 5, they were all oriented vertically. Right? Okay. Did you, I don't know if you can tell from your picture because I told you just to do a quick sketch, but for problem 2, where it says 2 plus 3 cosine, can you tell the furthest point, like how big is this shape? Like over here we said we went out 5. Can you tell on your picture how far out this went? Or can you figure it out from the equation? 5. How do we know it goes out 5? Well, you can tell maybe from your picture, but what's the biggest a cosine can be? The highest number a cosine can be is 1. So isn't the biggest this can be 2 plus 3? 5? Yeah. So you can kind of tell your size. And the reason I'm sharing that with you, what we're talking about that is, I had you set your window from -10 to 10 just so you could graph it, but graph everything. But in this one, if my biggest R is going to be 5, then I wouldn't need -10 to 10. I could get by with -6 to 6 or something like that. So by looking at your picture or your equation, you can kind of tell how big it is to help you set that window to get a good picture. And again, zoom square. If you're not liking what you're seeing, zoom square and you'll have the exact shape. All right, so we need to do a couple more things in our notes. So while we're here, let's go to the back of page 8. Back of page 8. We are going to sketch without a calculator. Now, again, you're not going to have to do this on the exam, but you do have to know what that looks like. So, look at your notes, look at what you did. What shape is this? Is this going to be a circle? Is it going to be one of the roses, one of the things with petals? Or is it going to be a lima sign, one of the things with it, like a lima bean shape? What is this?
Circle.
This is a circle. Right? is it a circle on the x-axis, or is it a circle on the y-axis? X. Is it on the right side or the left side of the x-axis? Left. And how far out is it going to go? What's this farthest point out here going to be? Six. Yeah, -6. See how easy that is? Based on what you know from looking at your picture. All right. Consider the equation 7 sine 3 theta. What things can you tell about the graph just by looking at the equation? Well, what shape is it? It's not a circle. It's a rose, right? It's what we call a rose, in petals. What can you tell me about the petals? There's 3 of them, and they are 7 long, right? We okay with that? Now, again, you are not going to have to sketch on the exam, but you've already given me an idea what it looks like. So now I'm going to fill in some values. So if I put in a 0, I'm just going to plot them as I go. If I put in a 0, I get 0. Good. What if I put in pi over 6? Pi over 6 would be right here. If I put in pi over 6, what do I get? This would be pi over 2. What's the sign of pi over 2? So that would be 7. So now remember, you told me this is a rose. So would you agree I've got something that looks like that? Without doing any more points, you can finish this picture. There are 3 petals. They are evenly spaced. Does that make sense to you? How far apart will they be if they are evenly spaced? 120 degrees, we're in radians, so we'll say 2 pi over 3. A full revolution is 2 pi. 2 pi divided by 3, that's how far apart they are. So if the first one is at pi over 6, where is the next one going to be? 2 pi over 3 later, which is 5 pi over 6. And where is the last one? 2 pi over 3 later. Which is 3 pi over 2. Now, freehand drawing, but there it is. Just based on what we have observed. All right, let's skip that last part and go to the back of page 9. Take a minute with your partner and see if you can fill in the table of values for number 1 and number 2. Some of you still need practice with your unit circle, so this will be some practice. think that's right. How do mine look compared to yours? They look okay? You don't have many points to work on, Parker.
On the pi is -4. Like, would that point not be like out here? Like,
No, because it's -4. So remember, that means you go the opposite direction. If it were +4, it would be out here.
Okay.
But here's angle pi
Yeah.
with a -r. Yeah, Sam?
How do you know how like big the loop is like in the first ones? I felt like when I was graphing last night, like the point where the loop is.
Here?
Yeah.
Okay, now there's no loop there. That's an indentation.
Okay. Oh, okay, I see. I read the top wrong, I get it.
So we got an indentation here. And the size of the loop will generally come out of your points. If there is a loop, when you plot your points, you'll see.
Like, how do you know how big like the arc from like each point is supposed to be? Like, I mean, I know you're just connecting them like in an arc, but like mine like looks a little bit different because I have the same points, but I just connect them.
Okay, well, first of all, everything is circular, so this looks like a triangle here, so you wanna make that's gotta be a circle. And there has to be an indentation, because I just told you to draw a circle, but it's not really a circle. So there has to be an indentation. This is a, sign problem, so the indentation is gonna be on the y-axis down here, so you just need to make sure you see the indentation. All right, we good? All right, we have one more problem to do in our notes. Let's back up and wrap this up. Problem, or example 6 on page 7. I don't think we got to this. Now that we've spent some time with our polar graphs, this actually may be an easier exercise. He drew it, but you would know before you started that that's what it looks like. All right, how would we know? Well, the leaves are, wait a minute. He's got a mistake. The leaves are not 6 long. That should be 3. On the scaling of the picture, that should be 6. He must have had a different equation, I don't know. Anyhow, that should be 3. So we know the leaves are 3 long. We know there are 3 of them. We know it has symmetry on the x-axis. So that picture makes perfectly good sense, right? Now, what's the question? If we only go from pi over 3 to 2 pi over 3, so if we only consider, here's pi over 3, and here's 2 pi over 3. If we only consider points plotted from here to here, so not all the way around we generate the whole picture. If we only consider that much, the portion of the graph consists of 2 pieces. One of those pieces is the portion of the graph in quadrant 3 from C, so this is point C, to D, which is a 4. Okay, so he's telling us from C to D, and then we have to finish it off. Well, you can do this really easily. You can either use your common sense as you're graphing, as you're graphing on the polar, watching your calculator graph, the way it goes from point to point to point, or you can actually plot the points. So if we put in pi over 3, then our R will be -3. So if we put in pi over 3, we have cosine pi, which is -1. So we get -3, which actually plots right here. Does that make sense to you? Okay, perfect. Now, what happens when we put in put in 2 pi over 3? What do we get when we put in 2 pi over 3? Well, that just gives us 3, doesn't it? Which is that point right there. So that point gave me -3. The next point I plotted gave me this. Those have to be connected. If you're confused, what's in between those two? Maybe pi over 2? What do we get when we put in pi over 2? A point in between. Don't we get 0? So there's the first piece of it, from C to D, and that's the order it goes, from C to D. And then there's the second piece of it, from D to whatever that is, A. So D to A. Goes in order from C to D, right here, that's C to D, and then D to A. That right there. When you do your polar graphs, you always plot them in order. So there's no skipping around. So we're going from here to here through D. All right, 314 is going to be due on Monday. I need to give you, have I already given you 315? I think so. Not you. All right, here we go, our last notes. Our last notes for this, yeah, this is it for our curriculum. So once we're done with 315, we start reviewing big time. Remember, you can always come to office hours and work on homework, check your homework, ask questions, review. Everybody get one? All right. One thing that is, I think, very helpful. 315 is about how polar graphs are changing. I think, and again, this is my own personal thing, it doesn't have to be how you approach it, but I often will draw the corresponding rectangular graph. So for example, if this is my polar graph, I would graph this. Because there are questions about increasing and decreasing. And to me, increasing is up and down, or that's up and down thing. And it's a little more confusing for me on the circular system. Now, you can do it, you guys are smart, you can figure that out. But I like to graph these things the old-fashioned way, and then I can clearly see I'm decreasing, positive decreasing, negative decreasing, negative increasing, positive increasing. It's easier for me on that picture than it is on the polar picture. Okay, so on page 1 of these notes, he kind of goes through all that. He's graphed the Rima-san, and then he's graphed the corresponding rectangular equation. So there's your polar, there's your rectangular, same equation. Now, we're gonna fill, for example 1, we're gonna fill this in. Where is our function? Positive and increasing. From what to what? Well, look at that thing. Where is it positive and increasing? From 0 to pi over 2. And then be careful, I think there's one more little spot. 11 pi over 6 to 2 pi. See how easy that is to tell on the rectangular graph? It is positive and increasing. All right, where is it positive and decreasing? Pi over 2 to 7 pi over 6. That is exactly right. Now, where is the function negative and increasing? 3 pi over 2 to 11 pi over 6. And where is it negative and decreasing? 7 pi over 6 to 3 pi over 2. All right, everybody okay? Now, let's look at the bottom. Even though he filled all that in, for some reason he filled it all in. I want to look particularly at the last set of boxes. They're all filled in for us, but I want to look at them anyway. So we're looking at our same picture, 1 plus 2 sine x. And we want to know, when is the distance between the function and the origin? What is happening to the distance between the function and the origin? As we go from A to B. So that's in the polar picture. It looks on the front page. So you can use the polar picture, or you can use your rectangular picture. From 0 to pi over 2, the distance from the origin, from the function to the origin, is increasing. Would you agree with that? You are getting further away from the origin. If you look at your polar picture, you're getting further away from the pole. You're moving out. Now, what about from pi over 2 to 7 pi over 6? What is happening to the distance? It's decreasing, isn't it? Now, on the rectangular system, we're talking about to the x-axis. So as we're coming down, we're getting closer to the x-axis. Be careful. 7 pi over 6 to 3 pi over 2, the distance is actually increasing. The curve is decreasing, but the distance from the x-axis or from the pole, if you're looking at the polar picture, is actually increasing. 3 pi over 2 to 11 pi over 6 is decreasing. The distance is decreasing. And then 11 pi over 6 to 2 pi, it's increasing. So we have to make a distinction between, is the function increasing or decreasing? And is its distance from the x-axis rectangularly or the pole polarly increasing or decreasing? Those are different questions. All right, next page. Number 2. He gives me a polar equation. I just told you I'm going to graph the rectangular equation. You don't have to. But to answer these questions, I'm going to do this. So what does this look like rectangularly? This is good review for us. What do we know about this equation? Midline is at 2. it's a negative cosine, which means it starts, a negative cosine has this shape, right? So I'm starting down, my amplitude is 4, so 1, 2, going up to 6, and down to negative 2. So it's gonna look like that. Does that make sense to you? And I know that my period is normal because I don't have anything there. So I know I'm gonna end out here at 2 pi. And I know right in the middle is gonna be pi. And I know this point right here is pi over 2. And this point right here is 3 pi over 2. Now, what I need to know is, if you read this, talk about things being positive and all that, I need to know what this is and what this is, because that's where I go from negative to positive, right? So I need to know, where does that thing equal 0? That will be where the cosine is 1/2. Did I do that right? Where is the cosine 1/2? Pi over 3 and 5 pi over 3? Are you keeping up with me, guys? My brain is moving, or is your brain moving? And that's important to me, not necessarily for the graph, but to answer these questions. All right, here we go. Which of the following statements is true about the distance between the point and, for me, the x-axis? All right, so here we go. From pi to 5 pi over 3, so from this stretch right here, from pi to 5 pi over 3, the function is positive, true, and increasing. Wait. Is that increasing? No. So A is out, not true. Every part of the statement has to be true. And I'm definitely positive, but I am not increasing. All right, let's look at B. F of theta is negative. Okay, so 5 pi over 3 to 2 pi. Is it negative? Yeah. Is it increasing? Ditch it. Not good. From pi to 5 pi over 3, it's positive, definitely. And it's decreasing, right? And is the distance to the x-axis also decreasing? Yes, so that's your true statement. C is your true statement. Now, I want you and your partner to work on 3. It's a little easier because he drew it for you already. So for example 3, the picture is drawn. See if you can figure out on which interval the distance to the origin, or the x-axis, the distance to the x-axis is decreasing. See if you can figure out which of those intervals that's true. And with the distance to be decreasing. Yeah. C. And again, the function, the answer is C. The function is actually increasing at that point, but the distance to the origin, or the distance to the x-axis, is decreasing. Does that make sense to you? All right, I'm gonna stop there Because I do want to hand your papers back, because I know some of you are distraught, or should be distraught. We aren't gonna go over them. Chloe hasn't even taken it yet. So Chloe, just go back and sit in the corner. But I want you to have a minute to look at it. If you want more time, like I said, come on in. Look at the phone, you best. You may talk about it with yourselves. Quietly and without too much specifics, because Chloe's back there. In fact, Chloe, why don't you just go sit out there? That way, we can talk a little more freely. Not that we have to, but. Oh, here's a purple paper right here.
He just grabbed that. I didn't see that. Listen, 5 years second. I can feel like if I saw my dad,
Feel free to consult Lydia. She's got all the answers.